All right, I think we have a good number of attendees join us. Welcome again to all of you to the webinar Driving Safety in Automotive Compute, co-hosted by Ignitarium and our long-standing partner MIPS. I'm Malvika, I'll be your host for the day. I'm the General Manager of Alliances and Partnerships for Ignitarium, and welcome again to all of you. The topic for today, as we all know, vehicles are becoming smarter and more connected, and compute platforms behind them must be built with safety at the core. So today we have automotive technology experts from both Ignitarium and MIPS dive into how cutting-edge compute is shaping the future of safe and intelligent mobility. So you'll see the table of contents here, some of the highlights being advancements in automotive compute, safety-first architecture and design principles, and practical insights and real-time interaction as well. Right, so before I can introduce the August speakers of today, I'd like to introduce the companies, MIPS and Ignitarium, who are co-hosting this webinar today. So MIPS, as we all might have heard, is a front runner in the innovation of advanced compute solutions that enable physical AI in autonomous automotive and industrial platforms. They combine high-performance real-time computing with functional safety and with their range of microcontrollers for autonomous platforms. Today, our speaker from MIPS is in fact going to be talking about one such microcontroller series, the M8500. I'd also like to introduce our own company, Ignitarium, here at this point. So we are an engineering R&D services company. Our existence is, we came into existence about 12 years ago. And our core services, engineering services, have started with semiconductor design. So we started with semiconductor design and we moved on to areas like embedded software, AI software, and cloud services. We have our offices and development centers in Bangalore, Kochi, and Chennai, and we service the markets of US, Europe, and Japan as well. So with that, I'd like to take a quick 30 seconds to brief you all about some housekeeping rules, laying the rules out there. So we will have a Q&A session at the end of this where the speakers will take questions from you. So you can put in your questions on chat and we'll pick up those questions and the speakers will be able to address them. We'll also have handouts. So we have some PDFs coming up during the session, which you can download and use for later reference. And if you guys are interested, you can come back to us with questions on that as well. And we'll also have a few polls coming up during the session to keep the session interactive. In fact, one might be popping up right now on the screen. And yeah, request you guys to please take the poll and submit your responses right now. I'll just give about 10 seconds for that poll. Thank you so much. Thanks, Balaji, for bringing up the poll. All right, so we get into who the speakers of the day are. Sean Murphy, welcome to him, Senior Staff Engineer, MIPS. Sean Murphy leads microcontroller product management at MIPS, and with 8 years of experience in the semiconductor industry, he has held various engineering and business roles and has a proven track record of creating innovative products. And at MIPS, he has turned his focus into the 32-bit IP space, as well as application-focused subsystems and silicon solutions. Welcome, Sean. We're very pleased and glad to have you here today. And to our speaker from Ignitarium, Santhi. Santhi is a VLSI design architect with over 22 years of industry experience. She specializes in IP and SoC design, verification and integration, functional safety management, and FPGA design and implementation. With her domain expertise in automotive SoC design and safety standards, she has led several functional safety and ISO 26262 projects for customers and delivered them successfully. She's coordinated with cross-functional teams to implement safety mechanisms and documentation on these projects. And demonstrating proficiency in RTL design, she also has proven expertise in performing third-party IP evaluation and integration to SOCs. So now, without further ado, we'll jump in and over to Sean, who will be our first speaker for the session. Thank you.
Hi, my name is Sean Murphy, and I am the product manager for our microcontroller products at MIPS. Today, I'm going to give you an update on our portfolio, as well as the functional safety strategy for those products. MIPS has been focusing on physical AI as the driving force in our portfolio strategy. That is because we see physical AI as an inflection point in the industry. Many companies are incorporating AI into their workflows, but physical AI is when we make it real. And in order to make it real, we need a combination of functionally safe compute, multimodal AI, and real-time compute. We divide physical AI problem space into three elements: sense, think, and act. Sense is where we are gathering data from potentially multiple sources such as cameras, LiDARs, and radars, and then moving that large amount of data upstream to where it will be processed. Think is where we are running our multimodal AI model in order to make a decision based on the current set of data. And now that we've made a decision, we need to act on it. So in act, we are actually interfacing with the physical world. For example, spinning a motor. And here's how those elements correspond to our portfolio of products. In sense, that includes safety-capable data movement engines for physical AI platforms. Products include P8700, I8500, and I8600 for applications like sensor fusion, networking subsystems, and data center infrastructure. In Think, these are edge AI acceleration for mixture of experts AI models. The first product in this family is S8200 for applications like real-time intelligence, industrial automation, and autonomous movement. And finally, in Act is where we interact with the physical world. And because we're interacting with the physical world, that demands high-performance real-time compute for applications like robotics and autonomous movement. M8500 is the first product in the Act family and is where I'm going to spend most of my time. And we really see Sense, Think, and Act in combination as the essential technology stack for physical AI. With M8500 specifically, we targeted real-time applications including motor control, digital power, and battery management. Many existing solutions use a combination of compute, such as general purpose cores, DSPs, or proprietary accelerators. And that can be either hard to program or even costly. So we created a unique architecture that combines a general purpose core with the right pieces of DSPs and accelerators to solve the real-time control problem in order to deliver a best of everything solution. And that unique architecture targets optimizing each step of the real-time control loop, including reading and writing from peripherals, interrupting the core, and processing an algorithm. And by optimizing this control loop, this can lead to advancements for real-time systems, including precise motor control in robotics and more efficient, smaller, and lighter power converters. It is also a 100% RISC-V compliant solution, which enables a general purpose programming model. There is also already wide ecosystem support for RISC-V, including vendor support for things like compilers, toolchains, and operating systems. Additionally, we are putting an emphasis on functional safety in this product. In real-time control, there are several applications in automotive and industrial. For example, in automotive, that includes things like traction inverters, which control the high voltage motor, onboard chargers, which charge the vehicle when it is plugged into, say, a wall outlet, DC-DC converters, which step down from high voltages to lower voltages, and battery management systems, which monitor the state of charge and state of health of the high voltage battery. Similarly, in industrial, we also see some motor control, digital power, and battery management applications, such as robotics, motor drives, and AC inverters for motor control, EV charging and solar inverters in digital power, as well as energy storage systems, which are really batteries that store energy in order to deliver power while the sun isn't shining in for example, solar applications. And due to the automotive trends, mega trends such as vehicle electrification and autonomous driving, there are already existing solutions in automotive that require high levels of functional safety. And this is actually something that MIPS has a strong heritage in the automotive functional safety side. And we are seeing a shift towards higher functional safety levels in industrial markets due to their megatrends such as Industry 4.0, humans and robots working together, as well as electrification on the industrial side. And when you think about these applications and trends, you can see why they're requiring higher levels of functional safety. For example, if I'm interacting with a robot on the factory floor, I should be able to interact with that robot in a way that doesn't harm me. Similarly, with electric vehicles, I need to be able to guarantee that when I put my foot on the pedal, the electric motor moves according exactly to how hard I'm pressing. Another critical part of functional safety is not only safe operation, but also being able to put the system into a safe state when it detects an error has occurred. So in conclusion, these applications and trends drive very high levels of functional safety, as well as a shift towards higher functional safety levels in the industrial side as well. These functional safety levels are defined by the standards, including in automotive ISO 26262, automotive safety integrity levels B and D, and in industrial, the IEC 61508 standard, which includes safety integrity levels of 2 and 3 in these applications. And you can see varying levels of functional safety level depending on, for example, the possible risk to human life. To achieve these levels of functional safety requires significant engineering design consideration and processes and procedures. Therefore, we have put an emphasis on functional safety into the M85-100 design and features. So in M8500, we start with our MIPS deterministic microarchitecture, which is based on RISC-V and is the RVM23 profile, which is a 32-bit microcontroller profile. Because of its application focus on real-time control, it delivers lowest latency control loops by having several unique features in the architecture. And those are targeted at each of the steps of the control loop, including reading and writing from peripherals, interrupting the core, and processing the algorithm. So we have features to accelerate real-time algorithms, minimize interrupt latencies, and deliver lowest latency access to peripherals, such as ADCs and PWMs that are critical for the control loop. We also offer tightly coupled memory in the system, and that's for two reasons. One, because it's extremely scalable, up from 0 to up to 8 megabytes of tightly coupled memory, as well as because it is deterministic and low latency in operation for those real-time control applications. So by having more memory local to the core, you're able to deliver very strong real-time performance for that critical section of code. We're also targeting 1 gigahertz frequency in the 22 nanometer node. And the reason we're targeting 22 nanometers specifically is because it is a high performance, ultra low power process, and due to its growing popularity, especially in automotive microcontrollers. And of course, we are supporting functional safety in this product up to ASIL D and SIL 3 when operated in lockstep. We also offer a number of other critical hardware functional safety features in order to achieve those high levels of functional safety, including things like ECC and parity on memories. Additionally, we offer some nice flexibility in the lockstep configuration, including supporting a dual-core split lock configuration, which allows you to operate two cores either independently or in lockstep with a primary core and a checker core, depending on your functional safety targets. And that is configured by the user at reset time. So it is not a permanent lockstep, but actually very flexible. Finally, we are really excited to announce that we will be providing reference silicon with our including our M8500 cores. This means we will be able to prove both the performance level and the functional safety of M8500 in silicon. Starting with this quarter, we will be offering the M8500 core in our virtual platform, which we call Atlas Explorer. Then later this year, we expect to have FPGA boards available as evaluation boards. And then finally, in the first half of next year, we will have reference silicon available in the form of a test chip. All of this is implemented in the 22 nanometer ultra-low process node, which also includes magnetic RAM or MRAM for code storage. From a real-time perspective, we will be able to demonstrate end-to-end performance in real-time applications, including with real-time peripherals such as ADCs and PWMs, in order to demonstrate the complete end-to-end control loop and actually demonstrate things like motor control and digital power in a real system. We will also be implementing SoC level functional safety concepts and features in order to deliver to customers reference silicon that is functional safety capable. So to wrap up, we are really excited at MIPS about M8500 and this year as we develop to continue to develop both the CPU IP and the reference silicon, especially to target functional safety critical applications. Thanks for the time, and now back to Ignitarium.
Thanks, Sean, for the great overview and the insights. Hi, I'm Santhi, Senior Principal Engineer at Ignitarium. Let's get into the functional safety dimension of the MIPS processor-based system, how we can ensure they not only perform well, but also meet the strict reliability and safety requirements needed in automotive and industrial use cases. Over the next few slides, I'll take you through the key safety building blocks from SCOOC concepts all the way to real-world certification readiness. SCOOC, or Safety Element Out of Context concept, is foundational when designing safety-capable systems using reusable IP, like the MIPS processor core. As we just saw, the MIPS processor-based IPs, or the SoCs, are being developed with safety-critical applications in mind. That's exactly where SCOOC comes into play. The idea here is we develop a component, in this case the MIPS processor system, independently of its final integration context. That means it's built with clear safety assumptions, fault detection mechanisms, and interface definitions upfront, even before knowing the exact system it's going into, whether it is an EV controller, an industrial robot, or a sensor hub. So why is this powerful? Number one, the reusability. We don't have to redesign or recertify the processor for each project. Number two, faster time to market. Safety collaterals like FMEDA and safety manuals come bundled with the IP. And number three, predictable integration, because we know what safety mechanisms are built in. So for MIPS processor system IP, with RISC-V architecture specifically, SCOOC is an ideal model. The open ISA gives you the flexibility, but also demands that safety considerations are modular and well documented. So when we talk about bringing safety into MIPS processor IP, SUOC is the structure that lets us scale, customize, and certify safely and efficiently. Let's shift gears and talk about where MIPS processor-based SOCs are being used, specifically in ADAS and autonomous driving, where functional safety is not just a requirement, it's a legal and operational necessity. At L1 and L2, we see driver assist features like lane keeping, emergency braking, and adaptive cruise control. These applications lean heavily on domain-specific accelerators and real-time microcontrollers, areas where the MIPS processor IP excels due to its customizability and low power profile. As we move into L3 and beyond, where vehicles begin to make decisions independently, the safety bar rises. You need redundant processing, hardware level virtualization, and deterministic performance. MIPS processors enables this with real-time cores, lockstep configurations, and the ability to integrate safety monitors natively into the instruction set. At L4 and L5, full autonomy introduces heterogeneous compute, AI accelerators, vision processors, control cores. MIPS processors modularity lets you tailor specific cores for failed operational behavior, sensor fusion, or safe state fallback. The big win here, we are not locked into a closed ecosystem. The RISC-V ISA, the instruction set architecture in the MIPS processors, allows third-party validation, transparent toolchains, and custom safety extensions, all critical for building certifiable systems without vendor constraints. Now, let's talk about how we make the MIPS processor core truly safety capable. The first and most well-known feature is dual core lockstep. This is where two identical cores run the exact same instructions in parallel. Their outputs are compared cycle by cycle. If there is a mismatch, a fault is flagged and the system can respond immediately. But that's just the start. We also add error correcting codes ECC on memory paths and interconnects. Watchdog timers to catch software hangups. Voltage, clock, and temperature monitors to ensure the physical conditions are safe. In the SOC, applying these mechanisms enables robust fault detection even at runtime. For example, integrating ECC with on-chip SRAMs or implementing clock monitors around peripheral domains helps to catch transient faults before they cascade. Now let's talk true redundancy. It's not just duplicating logic. It's about diversity and independence. We have the spatial redundancy and the temporal redundancy. Spatial redundancy means separating redundant logic physically to prevent common cause failures. Temporal redundancy means rerunning critical tasks to compare results at different times. Together, these approaches push diagnostic coverage beyond 99%, which is highly crucial for achieving a SIL D or SIL 3 or 4 certifications. Let's now look at the mean time between failures or the MTBF and why redundancy isn't just about safety, it's about uptime and reliability. MTBF tells us how long a system runs before experiencing a critical failure. The higher it is, the more robust our system is. For safety, this translates to fewer unexpected shutdowns, reduced hazard exposure, and better overall availability. Now, by implementing redundancy such as the lockstep cores or redundant memory controllers, we dramatically reduce the chance that a single fault can bring down the system. And this is highly critical in high-stake domains such as automotive and industrial robotics. Practically, we often see MTBF improve by 2x to 10x with architectural redundancy and proper fault handling. So the bottom line is redundancy is a strategic enabler for both safety and long-term reliability. Okay, so how do we prove all of this? It comes down to building a defensible safety case using well-established processes and evidence. Let's see few of the critical processes. 1. Fault injection testing. We simulate faults. How do we simulate faults? It can be a bit stuck at 0, a clock glitch, or a voltage dip, and then verify that our safety mechanisms catch them. This is where the rubber meets the road in validating safety logic. The next, we perform FMEDA, failure modes, effects, and diagnostic analysis. This is a quantitative breakdown of what can go wrong, what detects it, and how effective is that detection. FMEDA is usually paired with safety mechanism justification, where we explain why the selected approach is sufficient based on failure rates, conditions, and safety goals. These kind of analysis helps validate assumptions and align the safety mechanisms with the target SL level. It can be B or C or D. We also deal with tool qualification because if we are using automated tools in synthesis, verification, or FMEDA generation, we need to ensure those tools are trustworthy in a safety context. Finally, all of this ties back to compliance with ISO 26262 for automotive and IEC 61508 for industrial applications. So it's not just about building a safe SOC, it's about demonstrating it with data, processes, and structure. Okay, let's wrap up by zooming out to real world applications and the certification journey. In automotive, we are seeing MIPS processors based SOCs being deployed in ADAS controllers, battery management systems, powertrain and inverter controllers. These typically need SLC or D compliance. With pre-certified IP integrators can build on a solid foundation, one that includes safety manuals, FMEDAs, and diagnostic plans already validated. In industrial, MIPS processor-based SOCs are enabling robotics controllers, motor drives, power systems for grid and factory automation. These use cases often target SIL 2 or 3 under IEC 61508, and again, the modular rugged nature of the processor core IP makes it an efficient fit. And because leading risk-free IP providers are aligning with safety standards, integrators don't have to start from scratch. Instead, they inherit certification-ready artifacts, verified tool chains, and support for tool qualification workflows. Thanks for your time.
Hey, thanks so much, Sean. Thanks, Shanti, for that insightful session. I'm sure the audience now knows why the M8500 is suitable to their applications, the functional safety critical applications in both automotive and industrial automation. A quick poll is coming up on your screen right now. Don't go anywhere. Keep those questions coming on the chat. And soon after this, we'll have our Q&A as well. We'll just give that maybe 5 more seconds. We have people joining in. Yeah. All right. Thanks so much for your responses on this poll on functional safety, the areas that you face as the biggest challenge. We'll now share handouts. Like we said earlier, we have about I think 3 or 4 handouts that will be coming up on your chat. These are PDFs that you can download. Yeah. Should be coming up in the chat. And of course, you can, visit our websites of MIPS or Ignitarium.com to learn more about our functional safety offerings. It's all right there. And I think while we wait for the PDFs to come in, we can open up the floor for Q&A. I request the speakers, Santhi and Sean, to please unmute themselves and come on video and take any questions that the audience may have at this point. Okay, I got a question on the DM, so I'll just post it here. Can Sean, Shanti, can you see the question? Can SEOC be used effectively for mixed criticality systems with both safety and non-safety elements? That's the question on the end.
Yeah, yes, Malvika, I can take that.
Sure.
Okay, let me read out the question. So, can SEOC be used effectively for mixed criticality systems with both safety and non-safety elements? The answer is yes, absolutely. The safety element out of context is designed exactly for such scenarios, like allowing the IP to be developed independently of a specific system, yet still we can reuse it across safety and non-safety domains. So if we are using it in mixed criticality environments, these SEOC elements can be integrated with clear interface definitions and the safety assumptions along with the diagnostic coverage levels, so that allows a system integrator to combine them with other elements so that the SL level is also maintained accordingly. So the key here is to ensure the clear partitioning and then a strong documentation on the assumptions and limitations of each SEOC component. That way the functional safety package of individual components helps to get merged and get the required SL level. I hope that answers.
Thanks, Shanti. Any more questions that we may have coming? I think there's one from MIPS. Yeah? Sorry, go ahead.
Nothing. I was just saying, like, while we wait for the questions, are we going to flash the flyers on the screen from both MIPS
and I think they're on chat already, Shanti.
Okay.
There is one document. I think that's the checklist that we have for functional safety from Ignitarium. That's on the chat. Yeah, I have a question. I think this could be for MIPS on my DM. I'll just post it here. Sean, does MIPS have any functional safety certified devices on the market already? Yeah.
Yeah, very, very valid question. So MIPS has a very strong history of both non-safety and safety certified devices on the market, both in the original MIPS ISA, as well as now as we've transitioned to the RISC-V ISA. And we actually have on the RISC-V ISA, our P8700 product has completed certification up to ASIL B as in boy, and is one of the first high performance 64-bit RISC-V CPUs to achieve that level of a functional safety certification. So yes, we have a pretty rich history here, and we're continuing to invest in both automotive and industrial functional safety standards and certification.
Sure. Thanks, Sean. Are we seeing any more questions in the chat? All right. There's one I'm not sure who can answer this. I got it on here. You guys can read this, Sean, Shanti.
Yeah, so I'll read the question and maybe I'll start, and Shanti, feel free to fill in that if I miss anything after. So the question is, what do you provide to make functional safety certification easier at the system level? So as a CPU vendor, we bundle a functional safety package that includes tools like a functional safety manual, an FMEDA worksheet, as well as the certification itself that allow functional safety engineers at the system level to easily integrate into their system level functional safety concepts, and ties directly into what Shanti was talking about in terms of system element out of context, and that being an easier model to follow in terms of functional safety documentation and what we can flexibly provide to our customers to make it easier at their system integration level.
Yeah, that I agree with that. Additionally, it also reduces the time system integrators go for certification, because it's already bundled with its own safety package and the certifications. So it can be easily extended and integrated into the system.
Sure. Thanks, folks. I think we have the flyers coming in on the chat as well. So if you want to download those, I think you can. This is a good time to do that. I have another question, probably for MIPS. I think it says, how is MIPS positioning? 1 second, I'll just put that for my DM. Yeah, there you go. Sean, probably for you.
Sure, let me read it real quick. How is MIPS positioning in heterogeneous compute environments where AI accelerators and central fusion engines are involved? Yeah, so in the physical AI portfolio, as we divided that into sense, think, and act, we are adding into the think portfolio specifically where some of those AI accelerators and models are actually typically being run in existing products today. And we're going to be doing that starting with our S8200 product, which is going to be of course, a RISC-V based CPU, but then also adding hardware elements like vector and matrix multiplication into the CPU itself in order to have the hardware horsepower in terms of data parallelism to be able to compute AI models, as an example, And that'll be in in an environment that is typically done today by CPUs plus accelerators. So that's actually a pretty key part of our portfolio moving forward. And it is also why we are dividing the portfolio into the sense, think, and act like we are today.
Perfect. Are you seeing any more questions? Okay, we'll just give it a few seconds. Yeah. So do you guys want to post the flyers, and I guess we have the brochures and the handouts in the chat for you guys to download. All right. I'm not seeing any more questions. I think it's time to bring up our final poll, and there we go. All right. Thank you so much for those responses. Sean, Shanti, thank you very much. And to the audience for taking our time today. If you have any questions, please feel free to reach out to us on the mail IDs that we have on our websites, or just reach out to any of us through, the contact forms on our websites. Thank you so much. And we hope to see you again soon. Bye-bye.
Thanks, everybody. Thanks for the time.
Thanks, Erin.
Bye-bye. Thanks,
for
Sean.
everything. Bye.
Bye. Bye-bye.